Good morning, everyone. My name is Randy Hurst. I'm president of the Electricity Forum. Thank you for attending our session this morning, our live online forum on optimizing electric utility operations. Optimizing electric utility operations demands the best use of resources, and lack of optimization increases operating expenses and capital expenditures. It lengthens restoration time and response to environmental disasters. This is a very important issue these days in the T&D industry. And so I'm very glad that you've decided to join us for these presentations. Our first presentation is from CTC Global Corporation. David Townley's ready to go. If he could start your screen. David is Director of Public Policy, has more than 40 years experience in energy service and technology companies. His experience has been in both the regulated electric utility industry as well as the fast-paced electric technology development world. And I'd welcome David to the live online forum. And if you'd start, I'll get out of the way.
Very good, Randy. Thank you very much for that intro. I'm pleased to be with the Electricity Forum today. Before we get started on a relatively short presentation here, let's take just a moment to address the problem that we're going to be talking about today in this webinar. And the problem is rapid grid decarbonization. Now, the federal government already has a target of zero carbon from the electric grid by 2035, zero, and net zero from the US economy by 2050. Very ambitious goals. Most states are now preparing their state decarbonization plans. Many utilities have already committed to decarbonization goals, most of which are around a net zero by 2050 kind of target. Now, some of you may already be actively involved in these decarbonization goal plans, these plans that are being prepared either by the utility or by the state. But most of you will have actual impacts on the carbon emissions based on the choices you make regarding energy efficiency of the conductors you select for your T&D projects. And today we're going to talk a bit about advanced conductors and how they can be used in reconductoring the existing structures to actually contribute to rapid decarbonization. So what makes this link between reconductoring and decarbonization? We need more grid capacity. There's over 800,000 megawatts of generating capacity that is in queue, meaning they have submitted applications, they've asked the utilities for interconnection. There's no grid capacity, or they're waiting for that capacity to be made available. So we need more grid capacity to interconnect more clean generation so that that generation can run offsetting fossil fuel generation on a megawatt hour for megawatt hour basis. What I'm going to tell you about is reconductoring on the existing T&D structures with high efficiency advanced conductor is the fastest, lowest cost way to add substantial capacity to the existing grid. So what's an advanced conductor we're talking about here? An advanced conductor is just a modern design conductor that enables more current to flow over the same diameter conductor with less sag than the traditional conductor. And there are metal core type advanced conductors, and there are carbon or carbon composite core conductors as well. In this presentation, I'm going to talk about advanced conductors used for reconductoring, and I'm going to always be referring to this composite or carbon composite type advanced conductor. And I've shown a little picture there of at least 4 advanced conductors using this composite core that are available in the US. This composite core actually enables a very unique capability. That's why it's special. The composite core you see in the picture there replaces the conventional steel core in the traditional ACSR or other conventional type conductors. That composite core is much lighter, much stronger, much lower sag The thermal expansion is so much lower than the steel. It's so much lighter that even after you add more aluminum, and you can see here on the right is the trapezoid, aluminum is filling up all the holes. There's about 28% void when you use those round wires in an ACSR. When you fill those up, you got about 28% more aluminum. And the advanced conductors also use a more conductive annealed aluminum as well. So even after you add the aluminum, it turns out it's the same weight as the ACSR. And that's what enables a very unique capability in the current market, because these high efficiency advanced conductors can now be used on the same structure. That structure was designed for the weight of that ACSR of a certain diameter. And now it can be changed wire for wire on the existing structure and be able to bring much more capacity, much more efficiency to that right of way. So if you do reconductor, what do you get? Exchanging that wire, or in this picture, a group of wires, with high efficiency, high capacity advanced conductors using that same structure, you can get 50 to 100% more capacity now down that same right of way, depending on which technology you use and how the utility rates that right of way. As soon as you energize the line, though, you get a 20 to 40% lower line loss than the conductor that was on the structure previously. And because you're not rebuilding the towers, it's at least half the cost of the conventional structural rebuild in order to upgrade that line. And again, because you're not rebuilding the structures, you don't need the environmental permitting, the construction permitting. All of that is gone. In fact, you're using maintenance type practices for installation, the same kind of practices you might use for rebuilding after a storm. Those are the maintenance practices that you would use. And that enables you then to do a very fast process, because you don't need these permitting processes. You now can be in a 18-month, 24-month kind of max from the time you decide you're going to do it to the time you've installed and energized that line. And that line, because it's using these advanced conductors, are much, much lower sag. The picture on the right suggesting very little sag, which enables a number of different applications, but certainly enables a wildfire risk mitigation. We've seen that with anecdotal information, particularly out west. So where would you reconductor using advanced conductors? We talked about all the capacity that has applied for interconnection. That means that the utility is doing studies, load flow studies, to see, okay, if you connect up over here with this much capacity and it runs this way, where are my choke points going to be? Where's the congestion going to show up? Where do I have to do something? And what we're saying is that's the very place where you want to be reconductoring. Find those congestion points. That's the biggest bang for the buck. That's where you can increase grid capacity substantially. You can then get some generation interconnected, and that interconnected generation can have its output moved and distributed around the grid, offsetting fossil fuel and rapidly decarbonizing the grid. Now I want to turn to a study that came out now just 2 weeks ago from Grid Strategies, LLC. Their report was called Advanced Conductors on Existing Transmission Corridors to Accelerate Low-Cost Decarbonization. Very good report. There's a link. You'll get this after the presentation, and got a little hot link there for Grid Strategies report. And I invite you to take a look at it. Short, but very powerful. In that report, though, they did an analysis looking at just old lines, not counting what's the over 800,000 that has applied generation to get on and where that needs to be expanded, but just looking at old lines that are 50 years old and older. And they said there are over 200, conservatively, over 200,000 miles of transmission lines in the NERC regions that are going to be over 60 years old during the next decade. And if only 25% of those lines were reconductored with advanced conductors, then that would create enough capacity to interconnect about 270,000 megawatts of renewable generation, about 27 gigawatts a year. And that would enable about 2.4 billion metric tons of CO2 to be eliminated from the system. That's equivalent to about 22 very large base-loaded coal plants running for a decade, eliminating that much carbon. And for the consumer, looking at the installation plus the generation and its energy costs would reduce consumer electric bills by at least $140 billion over that decade. Very powerful, very important. So some recommendations for action that you can take. And I'm starting with the transmission owners, knowing the audience we're talking to here, many of you may be involved in the design and construction of distribution and transmission. Advanced conductors should be in all of your plans. You should be taking a look at what advanced conductors can do in your project, every project. And you should ensure that energy savings and carbon reduction are included in every T&D project evaluation. Now, some of these other actions are actions at the state regulator or at the federal level that actually would help you take less risk in making the choice to include advanced conductors around your system in all of your evaluations, and the energy savings and carbon reduction benefits to take those into account in your analysis and your project choices. For the state regulator, they should be looking at advanced conductors being deployed all through the system, anywhere the interconnection is being made. Reconductoring should be looked at as one of the first go-to choices to see if that works, if that makes a rapid capacity increase, enabling that new generation to come on. And that the regulator should shift from a least cost, lowest first cost or best lowest cost to a maximum net benefits when they're looking at this. That means bringing in energy savings to the consumer, carbon reduction to the environment. Those should be part of the benefits that are affecting the choice you make. So when they move to a net benefits, it enables you without risk to bring those other benefits into your decision making and make the right investment in the correct level of efficiency, line losses, carbon reduction, or the delay of more generation that's required to serve your load. You'll be delivering more from the generators that are interconnected. At the federal level, and we're working with FERC and DOE to have FERC again also highlight that advanced conductors should be the first go-to, should be reconductoring at all of these interconnection planning rules, and that efficiency should be a design criteria for every project. And at DOE, we're looking to establish, excuse me, to establish with them and through them a conductor efficiency standard, particularly one that's resistor-based, meaning that a certain amount, and we've suggested 10%, you need for any conductor you're going to consider for a project needs to be at least 10% lower resistance than your baseline. And typically that baseline is going to be an ACSR or a triple AC kind of product. So you always would be getting a more efficient conductor in that process. So what I've talked about is reconductoring with advanced conductors. You can use that to economically, rapidly interconnect more generation, and through that generation, accelerate decarbonizing the electric grid. And if you're involved in those plans, reconductoring should be one of those activities in every state and utility decarbonization plan. And so with that idea, I certainly open it up to any questions. We've got plenty of time. Be happy to answer some of your questions. And I presume, like other Zooms, you can put that in the chat section. And I see that there's a couple questions there.
That's great. Yes. Thanks very much, David, for the presentation. How do these advanced conductors perform in galloping and snow unloading situations when compared to ACSR? We now install twisted pair conductors.
Okay, and I will leave it to invite you to talk with our business development folks who can help actually run some studies with you to demonstrate this. But in general, this is a smoother surface, so you get less turbulent flow. It's a lower sag, so you get less blowout as well. So you should see less galloping, certainly less sag, and we have tested for those that do have and want protection. There's some adders that you put onto that line, of course, to reduce or change the frequency of that. But you can imagine the fact that it is that lower sag, you're going to have less opportunity for galloping. It's the smooth surface, and you have less blowout.
Okay, good question. Here's another one. Fewer line losses equate to what percentage of improved efficiency in terms of overall transmission?
For example, a 30% reduction in line losses would give you, let's say the T&D system, let's just look at the whole system. So you're running at a little below 6% overall. So a 30% reduction would give you 1-2% increase in the delivered electricity across those lines. So that sounds like a small percentage. That's a big number. It is a big number. And you can look at your own calculations of what that means in terms of energy savings and in terms of carbon reduction, depending on what your mix of resources are that you're moving across your grid. But it turns out to be a very significant number. And you can do that just by paying attention to the efficiency of the conductors you're using as you upgrade your system. And we'll be doing a lot of upgrading, of course, over the next decade.
I know that a lot of utilities are overloading their lines, correct? Instead of building new transmission. They do studies and then they overload their lines.
And I will comment on overloading is a real sensitivity, because overloading means increasing the current flow.
Right.
I squared R then is a square function. So as you're overloading that line, your heating is going up as a square, which means your sag, if you're using steel core,
right,
that's sag, you're going down.
Mm-hmm.
And your towers, of course, the size of your towers was, I'm going to run it at an emergency rating. It's going to sag this much with that current. I need a safety of this much.
Mm-hmm.
Voila, that's my tower. So when you start overloading, you're running the risk of actually safety violations and ground clearance violations to overload your line. In advanced conductors, I'll comment that even on the same structure, if you design that structure to fit the maximum loading of a ACSR or steel type core, these carbon cores or composite cores are going to sag so much less, even when overloaded 2x
mm-hmm.
times. So they can take 2x the flow down that corridor and not have any kind of clearance violations at all. So you pick up that opportunity to run it up to 2x. Many utilities will look at it, and depending on their load flow, load shape, and so on, we've seen from 40 to 65% is pretty common to uprate that right of way. But they still have, on top of that, what I would call flexible capacity, even on top of that for running whatever period of time they need. It's not an emergency rating for like, okay, I can do this for 2 hours, or I can do this for 200 hours over the life of no, these are rated. So you can run up at that 2x for an indefinite period of time, provided you've got the capacity to handle it in other parts of your system.
Okay, great. Okay, there was another question. How much increased grid capacities does this accommodate?
So on reconductoring,
That's sort of
or
the
even
same
new lines
question,
for that
isn't it?
matter, but still looking at reconductoring here, you're depending on the selection you make and how you as a utility are going to rate that. You'll see 40 to 65% is very common for an operating capacity increase, and we see that very often. So that increase of 50+% is very common. Again, you still get that flexible capacity above that if you need that in rerouting during emergency conditions, or you need to reroute power during fire or other natural disasters. You have that capability to run it at much higher levels, up to 2x, and not have safety violations, clearance violations, fire issues, safety issues with a low sagging line.
Okay, here's another one. Is the thermal rating of the free air cooling without spacing in the cabling the same cabling rating as typical cabling? Is there a difference?
I'm not sure I fully understand the question, but if it is if it's the thermal temperature ratings, go ahead.
Is the thermal rating of the free air cooling, I guess he means the free air cooling design without spacing in the cabling, is it the same cabling rating as typical cabling?
No, absolutely not. You can rate that cable, like I say, up to 2x in free air conditions. And again, often we see 40 to 65% increases in the rated, the typical operating rating of the equipment that's been reconductored or going in.
All right.
So no, much higher rating. Yeah.
Okay, great. The next one is you mentioned that the DC resistance of the advanced conductor shall be at least 10% less than the base conductor. At the same time, it is known that these advanced conductors are 3 times the cost of base conductors. Then what is the typical break-even period on average?
Good question, and let me address it in 2 ways. Let me address reconductoring first. In reconductoring, you pay a premium, and again, 3x is, I'll assume that, but it depends on the technology. It could be 1.5, it could be 4, depending on the size and which technology you're looking at. But let's say that it's 2 or 3 times. The fact that enables you to go on an existing structure for the weight design and be able to increase that capacity by 50%, 60%, that is the lowest cost. It's half the cost. So if you're talking about first cost, that's half the cost. And that's because that more expensive advanced conductor enables something that you couldn't do otherwise and get the efficiency. But let me address the efficiency then on a rebuild or even a new line. If you've got the same tower, just first off, it's lower sag. That means you can have towers further apart. You can have shorter towers. So there's some construction savings that you could have. Take that off the table for a moment. I build tower XYZ, and we've been building it for 50 years. That's what we're going to keep building. Okay, fine, great. Okay, I'm more expensive as a conductor. That first cost is going to go up now, right? Because that total project is going to go up. How much? It's going to go up on the order of, if again you use a 2 or 3%, it's going to go up 5%, maybe 10%. But I've got electricity savings. I've got carbon reduction. That when you begin to consider those, and again, that's not a first cost, revenue requirements, lowest cost solution. That is a debt benefits solution. When you bring that in, we often see that the energy savings alone on that lower resistance line that you get to use can often, in less than 2 years, pay back that delta between your conventional conductor and the advanced conductor. So when you take a look at that savings and energy alone, plus if you value carbon at all, you can certainly count the carbon, that becomes a very cost-effective solution. We argue before the FERC to say, when you use a least cost solution, you are forcing the consumer to pay 30, 40, 50 years of higher energy costs. That is not a just and reasonable rate if you don't consider that pile of money on the table that the consumer has to pay if you choose the lowest first cost and don't make the right investment in efficiency, versus making that efficiency investment and seeing that chunk of money go to the consumer over a 30, 40, 50-year period too, with a payback that is so short, on the order of months or years, couple years.
Great. Okay, next question. Any procedure adopted for thermal knee point reduction in ACCC?
Sorry, ask the question one more time.
Is there any procedure adopted for thermal knee point reduction in ACCC?
I'm not aware of any procedure that is used. I'm aware that knee point, when it goes through that change, it drops down onto the core, but that core is plenty strong, strong enough that again, it's stronger than the steel it's replacing. So the knee point, I've not heard a lot of this. I hear them talk about the knee point, the point when it sags down onto, or the aluminum relaxes onto the core, but the core is fully capable of handling all of that. It doesn't need the annealed aluminum, for example, to add some strength to reduce its sag. Not needed. That core is plenty strong to have that relaxation down onto the core, as well as the low sag to keep it up off the clearances, ground clearances.
Okay, great. And I think that was the last question that we had.